Welcome back, everyone. In this video, I will be continuing the implicit differentiation section. In the first video, we really talked about the technique of implicit differentiation, and then we use implicit differentiation to talk about the derivative formulas for the natural log and the inverse trig functions. Well, now we're just going to turn our focus to mainly practicing implicit differentiation. And for this first one here, we want to find dy over dx for the equation x times e to the y equals x minus y. All right, so the one thing you want to look at this is, maybe ask why we have to use implicit differentiation in the first place. Well, it's because we have y in many places and we cannot solve for it. There's actually absolutely no technique where you can possibly solve for y here, because in one spot, y is in an exponent from e, and the other one it's not. So there's no way to combine them at all. Because of that, we just have to use implicit differentiation, and without even thinking about more steps, you want to do the derivative of each side. And because we want dy over dx, you do d over dx of each side. Now, typically, I'm not going to try to trip you up at all and ask you to do dx over dy, but if you were asked dx over dy, you would do d over dy of each side. But whatever the bottom is, that's the one we want to do with respect to. Okay. So we got to do the derivative with respect to x of x e to the y equals, and then the derivative with respect to x of x minus y. So the derivative with respect to x of both sides. All right, now the left side can definitely look a little confusing first, but the one thing you want to think about is just visualize in your head if all the y's were x's. Well, maybe not this one because we get 0 here. But if this y was an x, what would you do? Hopefully you say, I'd use the product rule. Well, you still want to use the product rule because you're multiplying two functions, x and e to the y. And what does the product rule say? Once again, not trying to get overwhelmed about the fact that we have an x and a y. Just for the moment, pretend they're both x's. Well, we do the derivative of the first, so d over dx of x times the second, e to the y, plus the first, x, times the derivative of the second, e to the y. And that's how we set up the product rule. Right? I haven't used anything new. We just happen to have a y in there. And now the one on the right side, we talked about the derivative of just y before, so we can do this. The derivative with respect to x of x is 1. Minus the derivative with respect to x of y. That's what we call dy over dx. So at the end, just like from the above examples, we want to solve for dy over dx, but we're not necessarily done finding dy over dx everywhere, so you need to do all the derivatives first before you worry about trying to solve for it. All right, now do these other two derivatives. What is the derivative of x with respect to x? That's just 1. Actually, 1 times e to the y is just e to the y plus x. And what's the derivative with respect to x of e to the y? We actually did this exact one when we did the derivative for the natural log, but just kind of go through it in your head again. We start off doing the regular derivative rule. So the derivative of e to the x, if it was just x, is e to the x, but I have to make sure I use y. So the chain rule says, do the derivative, keep the inside, which is the exponent, the same, and then multiply by the derivative of the inside. And the inside, again, with an exponential function, the inside is the exponent. We multiply by dy over dx because the inside is y, and that's the derivative of y. Okay, so once again, maybe slow that down, maybe rewind the video and think about it again. Every time you get a y in here, you just do the derivative rule like normal pretty much, and then you multiply by dy over dx because of the chain rule. All right, so this equals 1 minus dy over dx. Now the point here is that we want to solve for dy over dx. This equation originally did not start with y equals, which means you're not going to do what we did last time, which is solve for dy over dx and try to plug back in. We're just going to directly do one thing. We're going to solve for dy over dx. And you have dy over dx here, and you have dy over dx here. If it helps, kind of pretend like dy over dx is like a third variable, like z. How would you solve this if you had z? Well, everything with z, you would get to one side, and everything without z, you would get to the other. But the same rule applies here. We want to take everything with dy over dx in it and get it to one side. So since they're on opposite sides, I'm going to add the dy over dx to make them both on the left side. Now, one thing is that when we solve for a variable, we want to get everything with it on one side, but everything that doesn't have it on the other side. So if I'm trying to get the dy over dx's to the left, this e to the y, which does not have an x in it, dy over dx in it, I need to get it to the other side. So I can subtract e to the y from each side as well. So that'll cancel. Right, now, on the left side, we have a bunch of mess, but if you just write it out, it's not too bad. We had e to the y, which is gone, and then x times e to the y times dy over dx, and we added the dy over dx, and this equals, on the right side, we had a 1, we got rid of that, and we subtracted e to the y. Right, doesn't look that great, but the point here, when you solve equations like this, when you have many letters and you're trying to solve for one of them, once again, if you're pretending this is z, you factor out the one you want to solve for after you get to this point. And we're going to go ahead and factor out dy over dx. Because at the end of the day, it is just a variable. It just happens to represent this thing called the derivative. And so when we take out the dy over dx, keep in mind that you cannot add them together here because this has some stuff attached to it. This only has a 1. There's no way to combine them. In the first term, you have x times e to the y. Oops, not x to the e to the y. X times e to the y. And then we have plus, and because we're not really adding anything, it's so visually a 1, we're adding 1 to it. And then the right side, we didn't do anything to, 1 minus e to the y. But then you can finish solving for dy over dx. Keep in mind, this is dy over dx times this. If we want to get rid of it, we divide by x e to the y plus 1. And we just do that to each side. And we'll have exactly what we want. We have dy over dx by itself. And it equals 1 minus e to the y over x e to the y plus 1. And that's our answer. Okay, your answer for dy over dx when you do implicit differentiation is going to have x's and y's in it. The only exception was, the two examples we did before to derive the derivative formulas, and that's because the original equations started off y equals. This one doesn't start off y equals, and there's no way to get y equals. So having y and x in our answer is fine. All right, so we did one. For the most part, we did really every technique you have to worry about here. We had some y's, we did the derivative, and we made sure we used the chain rule appropriately. We had a product rule, and you're never really going to see a quotient rule inside an implicit derivative because you can always get rid of fractions in an equation by multiplying through by the denominator. So having like x over e to the y would not be necessary by any means. We will see one example where it's unavoidable, but it's because you have to do the second derivative. All right, but the next one is pretty much the same. It's just using some different letters and different functions. The idea is going to be exactly the same. We want to find dz over dt for the equation z times cosine of t equals 3t squared plus 4z squared. Once again, you can't easily solve for the variable on top here, which is z. Okay, if we divide by cosine of t, that's great, but we have a z squared over here. So we cannot easily solve for z, which means we have to do implicit differentiation. And like I mentioned in the previous one, the dt is in the bottom here, which means when we do the derivative of each side, we do d over dt. See, cosine of t equals d over dt of 3t squared plus 4z squared. And once again, you have all those old derivative rules. So if you want to go ahead and just try to do this part faster, that's up to you, whatever you're comfortable with. Just don't forget that the z's don't match the t, so you're going to have the chain rule in there. All right, but on the left side, we have to use the product rule again because we have z, a function times a function, z times cosine of t. So let's go ahead and do that. Our product rule says do the derivative of the first, d over dt times z times the second times cosine of t, plus the first, z, times the derivative of the second, the derivative of cosine of t, equals, and now on the right side, the derivative of 3t squared, we can just use the normal power rule because it's t, and we get 6t, and then plus 4z squared. Well, we actually did one similar to this in the previous video. I talked about the derivative of y cubed. We still think about the power rule. If we had t here, what would the derivative be? It would be 8t. Well, because it's z, we get 8z. But by the chain rule, because t doesn't match z, we have to multiply by dz over dt. Okay, that's the inside part that we talked about quite a bit. All right, so just following the steps of last time, we want to make sure we do all the derivatives first before we start solving for dz over dt. Now, this one is just dz over dt because that's our name for it. We don't have a better name for this, and that's what we call it, times cosine of t plus z, and then the derivative of cosine of t, well, t matches just t, so the derivative of cosine is negative sine, equals 6t plus 8z times dz over dt. And maybe you were a little iffy to this point, but if you were able to get to this point, maybe try to pause the video and see, can you solve for dz over dt? All right, so to get dz over dt, we notice that dz over dt is in two of our expressions here. We want to get these on the same side. I'm going to go ahead and just rewrite this above. I can work right below it. I have on the left dz over dt times cosine of t. Now, if you want, a lot of people like to put it in front, which is fine. So cosine of t times z, dz over dt. And then plus z times negative sine would be negative z sine of t equals 6t plus 8z times dz over dt. And do exactly what I was describing before. Get the dz over dt's on one side and the rest on the other. So I'll subtract the 8z dz over dt to each side. Now, because I'm trying to get the dz over dt's onto the left side, I also want to make sure anything without these dz over dt, which the z sine of t does not have, get it over to the right side. I'll add that to the right side. And what are we left with? On the left, we have cosine of t, dz over dt, minus 8z times dz over dt equals the right side. The right side, we had 6t before, got rid of that, and then we also added z times sine of t. But it's really the same steps to solve once you get the main first step done. We factor out the dz over dt, and we have cosine of t minus 8z equals, and then the right side we're not doing anything to, just 6t plus z sine of t. And now we are just multiplying dz over dt by this. Remember, we're multiplying by this. It's not like we're plugging this in. We're multiplying by this. We divide each side by the cosine of t minus 8z, and that is our dz over dt. So dz over dt equals 6t plus z sine of t over cosine of t minus 8z. Pretty messy, yes. Pretty much when you do implicit differentiation, unless your equations are really short, they tend to have messy equations, but That's all there is to it. Now, one thing that you have to be careful on is when you use implicit differentiation, because your formulas have both letters in them, if you want to find the equation of a tangent line, or if you want to evaluate the derivative at a point, you have to have both coordinate pairs to plug in. And before, maybe we were given both x and y to find the equation of a tangent line, but we really only needed x and we could have figured out y by ourselves. Well, now we have to know both. So this next one says, use implicit differentiation to find the equation of the tangent line to the curve below at the point -3 square root of 3, that's x. We're using x's and y's, and then y is 1. Now, one thing I think is interesting is the way this graph looks. So what I wanted to go ahead and do is actually show it to you, because it's something called an asteroid. It's not an asteroid, but it's an asteroid. I'm not sure if Desmos can do it. So actually, if it doesn't work, then Wolfram Alpha will work. Actually, perfect. It does work. X to the 2/3 plus y to the 2/3 equals 4. And you get this diamond shape. It actually stops completely up here. You can't really click on it. I guess it's because it's not a y equals, but it actually stops up here. It doesn't go all the way up, all the way to the right, all the way down, or all the way to the left. So you just get this diamond shape called an asteroid. And what they're asking us to do is find the equation of the tangent line at this point where x is about -3 square root of 3 and y is 1. So that'd probably be around here, because this is about where y equals 1. So we want the equation of the tangent line there. All right. But the point is, actually, let me go back to the graph real quick. It doesn't pass the vertical line test, which means you're not going to be able to solve for y. Even though it's a much simpler looking equation than the previous two, we can't solve for y. We have to use implicit differentiation. All right, so let's go ahead and do that. To do implicit differentiation, we know we do the derivative of each side. And this one doesn't tell you find dy over dx, but we should know from our understanding of graphs that that's what we want. We want dy over dx. All right, we wouldn't want dx over dy because that's going to give us something else. So we want dy over dx. That means we're going to do the derivative with respect to x of both sides. And what's really nice about this one is that the right side is just a number. The derivative of a number is 0. Now, what about the derivative of the left side? Well, we're dealing with fractional exponents, but it's still at least just the power rule. The derivative of x to the 2/3, we bring the 2/3 down, we rewrite the x, and we subtract 1. 2/3 minus 1 is -1/3. Our exponent's 1/3. And then we know from previous problems already that the y is going to be pretty much the same. You still are using the power rule. So you bring the 2/3 down, rewrite the inside because it's really the chain rule. Subtract 1 from the power, it's still -1/3. But we know we got to multiply by dy over dx because y does not match x. So we're going to have our dy over dx. And if you forgot that, then really there would be absolutely no way to solve for dy over dx because it wouldn't be there. So that's another thing you can kind of use. Right? Now what we want to do is solve for this. Even though our exponents are messy, this one is much easier to solve for than the other ones because we only have dy over dx. We don't have another one and have to combine some stuff. Okay, so I want to go ahead and subtract this 2/3 x to the -1/3 on each side. I'm subtracting that because we only have dy over dx here, so every term without it I want on the other side. We got 2/3 y to the -1/3 times dy over dx equals -2/3 x to the -1/3. All right, now typically we don't want negative exponents and we'll take care of that, but I'm going to hold off until we get dy over dx by itself. All right, so what do we want to do here is now solve for dy over dx. You can divide each side by the thing that's multiplying dy over dx, which is the 2/3 y to the -1/3. So that's going to cancel exactly out with that. Now, the 2/3 also cancels out with the 2/3 because that's just a number, but there's no way to cancel anything here. X and Y are not the same. It doesn't matter if they have the same exponent, which they do. If X and Y are different variables, which they are, we cannot cancel. And what we're left with here, we have that negative sign here. I'll circle it because I know it got really small there. But we get dy over dx equals negative, and we have x to the negative 1/3 on top and y to the negative 1/3 on the bottom. And we have to plug in x and y. This is a big indicator that you should just go ahead and get positive exponents, because plugging in these numbers and then raising them to the negative 1/3 power is a little complicated. Now, whenever you have a negative exponent, you can just bring it to the opposite part of the fraction and it'll become positive. So we can bring the x down and it'll become positive 1/3 power. We can bring the y up and it'll also become the positive 1/3 power. We actually have our formula for dy over dx here. Now that's not all that we want. Of course, we want the derivative at this point. So we still have to plug in to get the slope. Plug in x equals negative 3 times the square root of 3, and y equals 1 to dy over dx. And you can see from the formula here why we need both x and y. So we get dy over dx, which will be the slope of our tangent line, negative y to the 1/3. We'll have 1 to the 1/3 over x, which is negative 3 square root of 3 to the 1/3. Okay, so we've got dy over dx. It looks exactly like that. Now, one thing is that the negative square root of 3 over 3 to the 1/3, if you put that in your calculator, it's not looking like it's going to help much. So how can we possibly help ourselves? Well, this isn't actually obvious at all. This is kind of a tricky thing, but you can simplify. Because we have 3 and the square root of 3, you can actually simplify this to one exponent. 3 times the square root of 3. 3, since there's not an exponent on it, it's invisibly written to the 1 power. And the square root of 3, the square root is invisible 1/2 power. And you should be comfortable with that by now. And since we have the same base here of 3, we can add the exponents, and 1 plus 1/2 is 3/2. Now, the reason why that's going to help us so much is if we're trying to simplify this. Now, the top is just 1. We have the negative sign, but 1 to any power is 1. This is negative. And then the 3 times the square root of 3 is 3 to the 3/2. And when we raise that to the 1/3 power, then we'll be good to go. So we got negative 1 over. Technically, you need to do the distribute the negative 1/3 power to each part. I know it doesn't look like much, but we technically have a negative 1 there, which is not being multiplied or raised to the 3/2 power. So you have negative 1 to the 1/3 times 3 to the 3/2, and then that's to the 1/3 power. Now, don't worry. I know this is the only one we plugged in to figure out the slope, but it's just because our formula is so messy. That's why this is confusing. Normally, you just plug it in and you're done. But we have negative 1 over, and now negative 1 to the 1/3 power. If you're not sure what that is, that makes sense because it's kind of odd. What you could do is just put it in your calculator. Negative 1 raised to the 1/3, but you should get negative 1. And of course, they do some craziness with complex numbers in Wolfram Alpha, but there you go, negative 1. Why? Because it's an odd root. If it's an odd root of negative 1, it's just negative 1. If it was the square root of negative 1, we'd have a problem because that would be I, but it's an odd root. So this is just negative 1. And then the exponent rule here says multiply the exponents. So the 3's will cancel, and we actually have 3 to the 1/2 power. Well, now we're almost done. simplifying this, the negative and negative cancel out, and the one on the bottom multiplying this isn't going to do anything. And then 3 to the 1/2, to kind of write it more simply, we can write it back as the square root of 3. So this slope here at this point, a whole bunch of work just to realize it's 1 over the square root of 3. But now you can simplify or get your final answer, because remember the equation of a tangent line, we use point slope form and we get y minus y1, that's 1, equals m. M is the 1 over the square root of 3, what we spent all this time doing, times x minus x1. X1 is this, because it's a double minus, we get a plus 3 times the square root of 3. And we can stop right there. Now you can simplify this. You can solve for y if you want. Distribute the 1 over the square root of 3 and add the 1 to each side. And I'll leave it up to you to check that we get y equals 1 over the square root of 3, x plus 4. And the only reason this simplifies so much is when you distribute the 1 over the square root of 3, it knocks this off. So you're just left with 3 plus 1 gets you 4. Right? But we'll stop here, and in the next video, hopefully we will finish up the last few problems I've got here in implicit differentiation, and also seeing our new derivative rules in action. I'll see you there.